So we have the basics of the game working now. The next thing we can do is to try to just double check that the physics of this code is correct. So the last thing I want to do is to have students out there, you guys out there, thinking that this code is all correct because Chris is such a smart guy and it looks complicated, so it must be correct. So the fact that something looks complicated almost never means that it's correct. It's really whether you check it to be correct. So you can actually check this code to make sure that this physics is correct. And what we can do is we can check to see that the number of seconds that elapses as this thing falls is what we would expect it to be. So to do that, we have to add a timer. And so I'm going to copy this to the clipboard. But there's actually not a copy code button for the t equals 0. We're just going to have to add that ourselves. And because it's a new variable, we need to put it up at the top. So it makes sense to put it next to dt. dt, by the way, is delta time. So it's the change in time for every time we run the draw function. So every time we run the draw function, just a little bit of time has elapsed. But initially, the total time is 0. So t is going to be our total time. And then we're going to paste in, we're going to write to the screen the total time. And I'm going to put it, I don't want to add anything after that line because then it won't run. But I'm going to add something like that there. So it's going to write to the screen what the time is. Okay, so there you go. And so 17.6 seconds is what it takes for the thing to fall to the ground. All right, so there you go. Now what we have to do is we have to figure out if this makes any kind of sense in terms of the physics. So, for example, what number did we expect it to take? How many seconds did we expect it to take as it falls to the ground? Well, we can think about this using this equation. So this is the equation for the height of something that is falling with a constant gravitational acceleration. So we need to use this to figure out how much time, basically to solve for how much time it's going to take for the thing to fall. And you might not have noticed it, but the initial height of the ship above the ground, if you look carefully at the program, at the very beginning, see how it says y equals 250? So that's going to be our initial height above the ground here. And then when it hits the ground, that's when y is going to be equal to 0. So that's going to be what we're going to do. Okay, so let's see. So this is the formula. Y of t equals the initial height above the ground. So in a second, we'll write that down as 250 plus the initial velocity in the y direction plus 1/2 gt squared. And here, g is 9.8 divided, g is minus 9.8 divided by 6 because it's 1/6 of the moon, 1/6 of the Earth's gravity. So I believe it is minus 1.63 meters per second squared. Okay? Now, initially in the program, at least, the velocity of the lander just starts at 0 and it starts falling, right? So if you look carefully at the program, you'll notice that, sorry, this is getting a little messy here. You'll notice that the velocity here is 0, especially the y velocity. And so what that means is that I can go back here and I can say, well, this is going to be 0. And so I don't even have to worry about this term. And then when it hits the ground, this whole thing is going to be equal to 0. And so now what I have to do is I have to solve for the time. Okay? So, so there we go. So we have y initial plus 1/2 gt equals 0 is what we get from all this. Sorry, my g's are not as gorgeous as they should be. And so let's see. I want to solve for the time. So what I'm going to do is I'm going to subtract 1/2 gt from both sides. So minus 1/2 gt squared minus 1/2 gt squared from both sides. Okay, so these cancel, and I get yi equals minus 1/2 gt squared. And now I can go ahead and put in some numbers. So I can say that, all right, well, initial y value, the height is 250, minus 1/2 times minus 1.63. So technically this is meters, and this is meters per second squared times the time squared. But you notice that there's a minus minus, right? So minus 1 times minus 1 is plus 1, so that turns into a plus. And now I can try to solve for t. And so I can do that by multiplying both sides by 2. So 2 times that. Then I can divide both sides by 1.63 meters per second squared. 1.63 meters per second squared. And so this gives us, so, all these things cancel out, right? And so this whole thing equals t squared is what we find. So this is t squared. So I could just evaluate this thing, take the square root. That should give us what we need. So if I do that, so 2 times 250 divided by 1.63, so that gives me, so let's write out, so t squared equals 500 meters over 1.63 meters per second squared. Okay? And then I'm going to take the square root of both sides, right? Square root of that. Square root of that. Whole thing. So t equals 17.6. Sorry, 17.514 or something. But basically, it's very close to 17.5. Okay? So from this calculation, we find that t is equal to 17.5. And do you remember what it was in the program? It was t equals 17.6. Okay? And so what's remarkable is that the number that it's supposed to be is only 0.1 away from what the program gave us. Now, is 0.1 seconds, is that a lot or a little bit? Well, consider that dt, the time step, is only 0.1. And so we got within one time step of what it was supposed to be. And another way of saying that is that we don't typically expect to get better times than what our time step is. So if our time step would have been 0.2, I would not be surprised if we were off by 0.2 here. So that's usually doing pretty good. If your time step is 0.1 and you're off by a second, well then now you're off by 10 time steps, and that's something fishy is going on there. There could be something wrong with your code. But so far, 17.5 seconds is what we get, and that seems to agree with the program. All right, so let me switch back to the program because there's some other fun things we can do with it. So I'm going to go ahead and erase this.